Hi everyone, I'm Mr. Fullerton, and today I want to talk to you about Coulomb's law, the electrical force between charged particles. Our objectives are going to be to use Coulomb's law to solve problems related to electrical force, to recognize that objects that are charged exert forces that can be both attractive and repulsive, and finally, to compare and contrast Newton's law of universal gravitation with Coulomb's law. There are some very big similarities there that can help us with our problem solving. So let's dive right in. Coulomb's law says that like charges repel each other and opposite charges attract. A positive and a positive charge will force each other apart. A positive and a negative will attract each other. Now, how big that force of attraction or repulsion is depends on two things. First off, the charge on the object. The more charge, the more electrostatic force. Now, they also depend on the distance between the charged objects. The closer they are, the stronger the force. The further apart they are, the weaker the force. And that's an inverse square relationship, just like when we talked about the law of gravitation. So our formula is the electrical force, Fe, equals K, a fudge factor, a constant, times charge 1, Q1, times charge 2, Q2, both of those in coulombs, divided by the square of the distance between them, R squared in meters. So let's see how this looks. The electrostatic constant, K, is given as 9 times 10 to the 9th Newton times meter squared per Coulomb squared. You'll also oftentimes see this written as 8.99 times 10 to the 9th Newton meters squared per Coulomb squared, which is perhaps slightly more accurate, but for our purposes and getting answers that are reasonably close, 9 times 10 to the 9th should suffice just fine. Now, graphing Coulomb's law, let's take a look at what happens to the electrostatic force as charge is increased, as one of the charges is increased. Because this is a linear relationship, as charge goes up, elect should go up. And if we also look at the electrostatic force compared to the distance between our charged objects, we have an inverse square relationship. This is proportional to 1 over r squared. Again, just like we saw with Newton's law of universal gravitation. Let's put some of this into practice. 3 protons are separated from a single electron by a distance of 1 micron, 1 times 10 to the minus 6 meters. Find the electrostatic force between them. Well, Q1, charge 1, is 3 protons, which will be 3 times 1.6 times 10 to the minus 19 coulombs, or 4.8 times 10 to the minus 19 coulombs. Q2, which is 1 electron, will be 1 times negative 1.6 times 10 to the minus 19 coulombs, or negative 1.6 times 10 to the minus 19 coulombs. So when we use Coulomb's law, electrostatic force is K times Q1 times Q2 over r squared, or 9 times 10 to the 9th Newton meters squared per Coulomb squared, times 4.8 10 to the minus 19 coulombs, times negative 1.6 times 10 to the minus 19 coulombs, all over 1 times 10 to the minus 6 meters squared. I run that through my calculator. I come up with the force of about negative 6.9 times 10 to the negative 16 newtons. Now, the magnitude of the force is what we're most concerned with here, which would be 6.9 times 10 to the minus 16 newtons. And we could look at it and say, yes, a negative force means that the objects are attracting. Or we could use common sense, look at the magnitude from from Coulomb's law, the electrostatic force, and realize since they're opposite charges, they must attract. So typically we worry more about the magnitude in going through these calculations and then determine later on whether they're attracting or repelling. Either case, 6.9 times 10 to the minus 16 newtons, and it's attractive because they are opposite charges. Question 2 says a distance of 1 meter separates the centers of 2 small charged spheres. The spheres exert gravitational force Fg and electrostatic force Fe on each other. If the distance between the sphere's centers is increased to 3 meters, so it's tripled, the gravitational force and the electrostatic force may be represented as, well, if their change, r goes from 1 meter to r equal to 3 meter, we have tripled r. And since our relationship for both gravity and the electrostatic force is proportional to 1 over r squared, since we tripled that, the change is going to be 1 over 3 squared, or 1/9. So we'll have Fg divided by 9 and Fe divided by 9. So both of those will be 1/9 of their original values. Answer 1 because of that inverse square law relationship. Another one here, we have a beam of electrons. So a bunch of electrons, negatively charged particles, is directed into the electric field between two oppositely charged parallel plates. The electrostatic force exerted on the electrons by the field is directed. Well, if we've got positive charges toward the top, the electrons are going to feel a force toward those, an attractive force. So they will feel a force in this direction due to the top plate. Now, due to the bottom plate, there's a negative charge. Negatives will repel a negative, so that's also going to push the charges toward the top. So overall, it will feel a net charge toward the top of the page. Answer number 4. Sample problem 4. The centers of two small charged particles are separated by a distance of 1.2 times 10 to the minus 4 meters. The charges are 8 times 10 to the minus 19 Coulomb and 4.8 times 10 to the minus 19 Coulomb. A. Calculate the size of the electrostatic force between the particles. Well, that's just applying Coulomb's law. Fe equals K Q1 Q2 over r squared, or 9 times 10 to the 9th Newton meters squared per Coulomb squared, times our first charge, 8 times 10 to the minus 19 coulombs, times our second charge, 4.8 times 10 to the minus 19 coulombs, all divided by the square of the distance between them, 1.2 times 10 to the minus 4 meters squared. Run through that calculation, and I come up with a force of about 2.4 times 10 to the minus 19 newtons. So there's the size or magnitude of our force. Next, we're asked to graph the relationship between the magnitude of the electrostatic force and the distance between the centers of the particles. So that'll be the electrostatic force on our y-axis and the distance between them, r, on our x-axis. And we know since this is an inverse square law, it'll have that shape where it's proportional to 1 over r squared. Hopefully this was helpful, gets you started on Coulomb's law and the electrostatic force. And if you have questions, need more help, check out aplusphysics.com. Thanks for your time and make it a great day.